let's talk about probability. So, what is probability? Exciting, right? So basically, probability is the study of random events, right? So if you took a class like physics, right, you learned a lot about these kind of immutable physical laws, right? So probability is not something like, you know, F equals ma or E equals IR, right? These things are kind of fundamental relationships between quantities that are not random at all, right? So if you have a given I and a given R and you multiply them together, you always get the same E, right? Now, in electrical engineering, as you're going to see, we have lots of situations where the situation is much more fluid, right? Where we don't get exactly a known result from a given experiment, right? So basically, probability is, at its heart, the study of random experiments. And what I mean by that is that you have a potentially different outcome every time. And so this probability, you know, formalism, oh, you can take off if you want. Okay, so this probability formalism is used in lots and lots of real-world applications. So I mean, this is not a slam on signals and systems, but unlike signals, where maybe the concepts sometimes seem a little bit abstract, probability has like many immediate understandable applications, right? So certainly, you know, the most obvious one is, you know, gambling, games of chance, right? But more realistically, you know, a more advanced form of gambling is the financial markets, right? So we model a stock price, so we figure out which way it's going to go, or we're doing some sort of like option pricing or commodity pricing, right? The stock price of a given asset is uncertain, right? And it's governed by lots of weird market forces plus a bunch of randomness. So we don't know what's going to happen the next day, but the whole point of people on Wall Street is to kind of predict and you know, anticipate what's going to happen, right? Certainly in terms of like testing and consumer safety. So, you know, manufacturers release products all the time, you know, cars and computers and stuff that they know have, you know, very, very unlikely bugs. And so, you know, when do you think it is statistically safe to release a car, right? So people are making judgments about, you know, I know there's a bug, but what is the probability that this bug is ever realized in a zillion trials of a product, right? So that has real implications for when you release a product, how you price a product. So simulation is a big deal. So simulation of large systems, right? So how do we, you know, model or understand some sort of a concept that is impossible for us to observe directly, right? So like, you know, what are the weather patterns like, or what's going on inside a molecule, stuff like that. In those cases, we run a simulation and we add some random noise to kind of account for the uncertainty of the process that we don't really understand. So simulation basically is all about probability. Kind of more, you know, boring but important stuff is like actuarial sciences and insurance. So, you know, when I go out to get car insurance, right, how do I know, you know, how does the insurance company know what a fair price, well, maybe fair is the wrong word, what a profitable price is to charge the client? You know, they're trying to give you a price where they're going to make a sizable profit, assuming that you don't get into an accident, right? So that's based on your age and your gender and your risk factors and where you live and whether it snows and all that stuff. More appropriate for us electrical and computer engineers is, you know, signal and image processing. I'm going to say a little bit more about some specific examples there in just a second. So I'm an image processing computer vision researcher by trade, and so we use random numbers all the time in our modeling of how images are formed and segmentation and classification and things like that. Communication systems. So communication systems, information theory. These are courses that you're going to see in your next level classes, your junior and senior level classes, that depend fundamentally on the stuff that we're going to talk about in this class, right? And, you know, things like networking. So wireless networks, even wired networks like, you know, packet switching, and so on. And finally, machine learning. I know everyone wants to know about deep learning and all that kind of thing. So, it's really hard to understand what's fundamentally going on in a machine learning algorithm without having a deep basic understanding of probability. So I think that, the stuff you're going to learn in this class will hopefully have wide-ranging applications for you as electrical and computer engineers. So let me go into a couple more examples that are really drawn from the EE CSE world, right? So an important one is, a communications network. So let me kind of sketch out here. You can already see there's going to be a issue with seepage of my pen. So let's draw it like this, actually. So I have a information source. And that goes into some sort of a transmitter. And that produces a signal. And that signal goes through some sort of a channel. So for example, you send a text, right? You type the stuff into your phone, and then you press send, and somehow that goes through either the Wi-Fi network or the cell network out into the world, and that channel then, the stuff that goes through the channel gets received at some sort of a receiver. And then this is like the information destination. And so this basic model, encapsulates all sorts of communication processes, right? Cell phones, wireless networks like Wi-Fi, television, like either over the air or cable TV, satellite transmissions like satellite TV or satellite transmissions coming down from space, even wired packet networks like internet or LANs, right? And the fundamental issue is that there's always some difference, whether you perceive it or not, between what gets sent and what gets received, because the channel is messing up the signal in some unknown way, okay? So, for example, why does the channel mess up a signal? So one possibility is that you're doing some sort of satellite imaging, or even imaging within like a big city like New York, right? And so what happens is that there's atmospheric interference, right? So the weather that's going on may corrupt the bits that are getting sent through the ether there. There's something called fading, which means that the signal is not as strong where it gets sent as it is where it gets received. There's thermal noise or electrical noise. So if you're modeling, voltages and currents inside of a circuit, where that circuit is with respect to big pieces of metal and stuff in the room or solar radiation, stuff like that, can affect the fidelity of information that's traveling down these tiny wires, right? If you're in a audio processing application, you could have acoustical noise, right? So like I'm talking, but there's the HVAC system that is making some sort of a, steady hum, right? Or a big ka-chung. And so what happens is that, even though I know purely what's going into my wireless mic, what comes out of the speakers is that plus some sort of a noise, right? Kind of related to that is what I would call like compression, right? So in order to take a audio or a video sequence and send that compactly over the internet, you have to compress it, right? So, I mean, if you think about how much space, one of my first image processing exercises is, how much information is contained in a raw DVD or Blu-ray of a movie, right? And it turns out to be, hundreds of gigabytes, right? Yet, clearly, your ISP is not sending you hundreds of gigabytes when you watch a Netflix stream, right? So there's serious compression going on, which means that the pixel value that you sent through the channel is not really the pixel value that you're seeing on your TV, right? That means that there's some difference, some quantization noise, and you can model that with probability, right? There's also crosstalk, right? So if you're sending a bunch of signals and those signals are going down wires that are all parallel to each other, there can be some interference between what's going down wire A and what's going down wire B, which is wire A's neighbor, right? So things get kind of messed up. In image processing, which is something that I do, there's what's, for example, in older movies, you see what's called film grain, right? So maybe you have a beautiful image that you see through your camera viewfinder. When you capture that image because of, for example, low light or something like that, you get this kind of muddy, grainy thing, which is maybe kind of cool for artistic effects, but it's not really what you put into the camera, right? So there's a difference between the input and the output that's unknown and hard to know deterministically, right? And so if we're to simplify this in a super simplified way, for example, suppose that I send out some, signal. I hope that what comes out is the same thing, but what may actually get through the channel could be, some sort of corruption, right? Where these bits here got flipped by the channel, right? And there's a certain probability of that kind of thing happening. And so if I were to kind of make, a more detailed description of this, I could say something like, on the input side, I have, either 0 or 1 coming in, and I hope that 0 goes to 0 and that 1 goes to 1, but there's also a probability that I can get some sort of flip, right? And so maybe with probability epsilon, I flip, and with probability 1 minus epsilon, I stay where I am. This is a pretty common model for how real-world communication channels work. And you hope that your epsilon is super, super small, right? Otherwise, you'd have a really big problem. And so you want to ask questions like, what is the probability that a 0 is sent, given that a 0 is received? Right? How much can you trust the bits that come back at you across the channel, right? How can we modify the coder to decrease the error rate? So a really kind of naive way of thinking about this would be say, okay, well, if I've got a really noisy channel that's flipping all my bits, maybe what I should do is if I want to send a 0, I instead send 3 zeros across the channel. And I hope that when I take the majority vote for what comes on the other side, that I get the 0 that I sent in, right? So you could kind of imagine that there's some sort of like error correction or robustness to the channel. And then I could study, well, obviously that means I'm sending 3 times less information. How much information can I push through that kind of thing, right? So we're not going to talk explicitly about those kinds of problems here, but that's the kind of stuff that you would study in a course like communication systems or information theory. Or you could say, so basically, in general, we want to talk about the expected performance of different strategies. So, I could imagine I could send the same bit 3 times, or I could send the same bit twice, right? What would be better, right? Probabilistically or statistically. Another, possibility would be something that's a little bit more like a big machine, right? So say you've got some sort of really complex system. Where kind of the, the flow through of the system is governed by, some stuff that's in series and stuff that's in parallel. So imagine that these are components. So I've got, something like this. And so you might imagine that, for example, these are like parts of Amazon's crazy cloud storage or web server or something like that, where there are some things that are in serial and some things that are redundant in parallel. And then I can ask questions like, each of these has some sort of probability of failure in T hours. And then I can ask something like, what is the expected time to failure of the whole system, right? So clearly, if C4 fails, I'm still okay because I've got C5 as a backup. If both C4 and C5 fail, well, then it's okay because I've still got the top branch where C2 is still working. But if C2 and C3 both fail, then I'm stuck, right? So I can ask questions like that. Given that each of these things has an independent time to failure, what could happen, right? Or I could ask more detailed questions like, what's the probability that 3 of the 6 components fail in the same weekend? Right? So you've got your IT staff, they need to be on call, and you want to know, how much should I be paying the staff and how many people should I have on retainer, because if something goes wrong and they need to fix these things, how likely of an event is that, right? That has implications for the finance side, it has implications for how much you pay these people. Or you could say, you know, if C2 goes down, you know, how much longer will the system last? Right? So this is kind of a question of what's called conditional probability, right? So if this happens, then how does that change the probability of other things, right? Which again is a real world system kind of problem where, you know, you've got a real world thing and suddenly this component breaks. You can't order a part for another 2 weeks. So how much, you know, will your system last that 2 weeks, or do you have to find another supplier, right? Okay, so let's talk a little bit about a more networky kind of thing. So if you take a course like computer networks, you're going to learn all about the fact that, you know, when you send, for example, a text message, it's not actually, you know, going in one big chunk of data, right? It's probably getting split up into a bunch of little small packets that are being handled by a router somewhere, right? So kind of in the real world, kind of what happens is that we've got all the users on the RPI Wi-Fi network, for example. And all of you are competing for Wi-Fi resources, right? And so you're all sending packets to our poor overloaded servers and routers. And you know, that router is going to mostly do its job, right? This router basically sends stuff out into the world, but you know, it has a buffer. So basically what happens is that every packet that arrives gets kind of a first come, first serve, you know, position in this buffer. And so, you know, life is good when the buffer is big enough to handle all the traffic, but you know, the buffer has a finite length, right? So you can ask questions like, okay, what's the probability that 10 packets arrive in the same 10 millisecond interval? Right? So, you know, obviously the system is not going to work if everyone is transmitting lots of data all the time, right? The kind of assumption is that of the 100 of you in this classroom, maybe only 30 of you are actively transmitting data, right? And those 30 people are switching as we go across the, you know, span of this class, you know, but we don't have full usage all the time. So we kind of want to know what's the probability that suddenly the network gets clogged with lots of stuff. And in the worst case, we could ask basically, like, what's the probability of the dreaded buffer overflow, right? That's really bad because then packets are actually lost, right? So you send your text and it doesn't get through because it never gets to the router because the router is overwhelmed, right? Or you could ask questions like, you know, what's the probability that greater than 80% of the network traffic is from, you know, one user, right? So this is like, you know, who is torrenting in their dorm room, right? You know, I find out that all this data is coming from one place. Is that likely to be random chance, or is that likely to be bad behavior, right? And you can also think about this like traffic modeling, right? So is it more likely that this crazy usage is due to torrenting activity or due to downloading a Steam game that's 4.8 gigabytes, right? So, you know, the shape of the traffic maybe has an implication for, you know, probabilistically that you can tell the difference between those two things, right? So for sure, RPI is doing this kind of thing. There's also, as a side note, we'll talk about things like, you know, spam filtering, right? What's the probability that this mail that comes to me from, you know, some overseas country is a true mail or it's a spam mail, right? That's what your respite spam filter is supposed to do, right? Is to kind of make a good probabilistic guess about what is real and what is not, right? And hopefully it does a good job, but if it doesn't, you keep on training it by dragging good mails out of the spam box and bad mails into the spam box until it gets a better estimate of what's going on, right? And the final thing I guess I'll say is, you know, machine learning type stuff, right? So all this kind of stuff maybe seems a little bit more old school, perhaps, but I can tell you that all the people at Facebook and Amazon and Google care a lot about probability because it's really important for machine learning. And so, you know, especially in things that happen all the time right now, like you know, speech recognition, image classification. So, for example, if you are talking to your Amazon Echo and it's trying to figure out what you're saying, right? You may have a model for the probability that this given speech waveform equals, you know, the word Polytechnic, right? So again, the raw input is the raw audio that your echo is hearing, and then that has to get translated to actual words, right? And then you may have a problem that's more like, what is the probability that, you know, this raw waveform at time I was Polytechnic, given that the waveform at time I minus 1 was Rensselaer, right? Clearly, somehow, that probability is a lot higher than the probability of Polytechnic occurring by itself, right? So this conditional probability of kind of modeling not only at a word level, but even at a phoneme level, right? So if I'm saying Polytechnic, right? So I mean, there's only so many things if I say Pol and it's anticipating what's the next syllable or the next phoneme likely to be, right? That's a probabilistic thing that's built up from models of the language. So it may be different in English than it is in Mandarin, right? Because the syllables that occur are all different, right? Certainly in terms of kind of like, you know, facial recognition type stuff. So in Facebook, you're, you know, looking to see what's the probability that this, you know, first there's a face detection algorithm for what's the probability that this patch of pixels contains a face, and there's a second layer of what's the probability that this face belongs to one of your Facebook friends, right? And then there's also kind of the more general question of, you know, the probability that this image, you know, contains a cat, right? So, you know, clearly there's lots and lots of really sophisticated machine learning algorithms going on. You can take Professor G's deep learning course to learn about the state of the art in machine learning. But he's teaching a course right now called probabilistic graphical models, right? Which is kind of, again, underpinnings of machine learning. And you won't be able to make heads or tails of that course if you don't take this course, right? So hopefully I've kind of motivated why probability is important. I mean, I think that it's pretty easy to see that there are many, many applications for why you need to know how this stuff can be modeled, right? So there's kind of a modeling problem of what's the best, you know, for example, we're talking about packets arriving at a switch, right? You know, do those packets arrive like a heartbeat regularly? Well, probably not, right? They probably arrive in some sort of a more random fashion where there's sometimes a burst of packets and there's a big span where nothing happens and another burst, right? So what's the right model for packet arrival? And then once I know that model, how can I answer questions like, you know, what's the probability that 50 packets arrive in this interval, right? So we're going to talk about a little bit of both of these things, how to model things with the right probability model, and then how to analyze them with the right probability tools, okay? Now, many times, even though we've talked about all these kind of like real world systems, you know, probability can often be boiled down to some very simple kind of ideas. And I'm sure that you've probably seen these ideas long ago, right? So we can often kind of boil this ideas down to, you know, we can flip a coin, right? And look at heads versus tails. We can roll a die that has, you know, a bunch of outcomes. We can pick a ball out of a urn. So, urn. An urn is basically like a jar, but it's opaque, so you can't see what's inside. I guess that's why I didn't call it a jar. So basically, you know, these kinds of very simple things, right, can actually be used to build up into some fairly sophisticated problems, right? So you will find that in the homeworks, I'm going to do a lot less die rolling and urn picking and a lot more kind of, you know, Thanos snapping and Overwatch teaming. So hopefully you'll be able to see that there's a lot of real world applications, maybe not the Thanos snapping, that can be mapped onto these concepts that you're going to learn here, okay? And so what I want to talk about for the rest of the time is basically the building blocks of the terminology that we need to even start talking about probability. We're not going to compute any probabilities today, and maybe not even next time. We're going to talk more about, like, what does it even mean to talk about probability? Okay, so let's talk about the fundamental, you know, concepts. So key probability terminology. And that's what homework 1 is basically all about. Okay. First thing that's important is what's called an experiment. So basically, an experiment is some sort of procedure and a resulting measurement. So let's give some examples, right? So for example, let's talk in the world of, rolling dice and flipping coins, right? So let's suppose that I, roll a 6-sided die, d6, and I count the spots, right? So that tells me what to do, roll the die, and then how to get a outcome or a number out of it, right? Or I could roll 2 d6 dice and count the sum of the dots. Or I could, roll the 2 dice and I could report the outcome as a 2D vector, right? So instead of adding the numbers up, I ask you what was die number 1 and what was die number 2, okay? Or I could, toss a coin 5 times, count the number of heads. Or I could keep tossing the coin until I get the head. And then I record what number that happened on. So in this case, I could get it on toss 2, I could get it on toss 108, I could get it on toss 10,000, right? I could, toss the coin 3 times, and I could record the pattern. Let me just switch my things here. So these are all basically things that will give me, if you think about it, something that's like a discrete outcome, right? 1 or 0, or a natural number, or H or T, or a pattern of those things that I can basically count on my fingers what the outcomes are, right? But there are also experiments I could do that will result in a continuous number, right? So I could say, for example, pick a random number between 0 and 1. Or I could, measure the lifetime of my hard drive in days or minutes or whatever. And finally, I could do something like, pick a number x at random in 0, 1 in that interval, and then pick another y in the range of 0 to x. And so here's a procedure where I do something first, and then the next thing I do is contingent on that first outcome, okay? So things to observe about all this list of stuff, right? So these experiments can result in something that is either discrete, like numbers 1 through 6, right? Or continuous, right? So here, for example, the random number could be, pi over 4, right? Some sort of infinitely repeating number, right? You could have either a finite number of outcomes or an infinite number of outcomes, right? So for example, there's only 6 possibilities for E1, but there's, 36 possibilities for E3. Or there's an infinite number of possibilities for E5, right? You can have the same procedure, but also have different ways of measuring what happens, so different outcomes. So for example, E2 and E3 are fundamentally the same thing, roll the 2 dice, but they have very different possibilities for what happens, right? So in one case, the outcomes are from 2 to 12, and the other case, the outcomes are a set of 36 two-dimensional vectors, right? And finally, like in the case of E9, E9 is basically something where the outcomes are contingent on a series of experiments that are all somehow linked together, right? So I have to wait to see what happens in the first choice of X before I know even how to pick out Y, okay? So experiment. That's the key first topic, right? So term number 2 is what's called the sample space, right? So the sample space is basically the set of all the possible things that could happen. Okay, so let me write that down. So the sample space. So the sample space is basically the set of all possible outcomes. So exactly one outcome from the sample space occurs on each experiment. So only, I basically enumerate all the possible things that could happen on the experiment, right? So let's take, for example, E1. So what is the sample space that corresponds to that experiment, right? So usually what we do is we write the sample space. I'm just trying something different here with this pen. So basically, what are the possible things that could happen? I make a list, and I put them in curly braces, right? So 1 through 6 are my possibilities. I put them in curly braces to make it clear that the order of these things in this set doesn't matter because it's a set, not a sequence of things, right? What are the things that can happen in the second experiment? Well, I could get, the lowest number I could get would be 2 1s, snake eyes, and so I get 2. And then I could get all the numbers up to double 6s, right? So there are 11 outcomes in that set. Like we were talking about, for the third experiment, I have the same procedure, but instead my outcomes look like a set of vectors, right? So I basically go all the way up to 1, 6, and then I go all the way down to this. So I have 36 elements in the sample space there. So I pause and ask for a second, because I'm new to this classroom. What do we think of fat pen versus thin pen? Who votes for fat pen? Who votes for thin pen? All right. Fat pen. All right, thin pen it is. Maybe I'll try and get some sort of happy balance between fat pen and thin pen. And I just bought these fat pens this morning. All right. It's all right. I aim to please. So let's take a look at E4. So sample space for that, toss the coin 5 times, count the number of heads. Well, I could get 0 heads, I could get 1 head, I could go all the way up to 5 heads, right? Sample space for experiment 5, keep on tossing the coin until I get the head and record that toss number. So I have to have at least 1 toss, right? So certainly this starts at 1. It may take me 2 tosses, 3 tosses, but this number goes on forever, right? So there is no upper bound to the number of tosses that it may take me to get that first head. If I'm looking for a pattern, right, so I toss the coin 3 times, I record the head-tail pattern. And so again, there are 8 ways this can happen, right? So I could get, head, 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 tail, tail, head, head, tail, head, tail, 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 head, tail, tail, tail. I'm sure I missed something. Head, tail, tail, head, tail, head, right? So there are 8 distinct outcomes. And as you'll find out, not on this homework, but on a future homework, one part of probability is understanding how to count the number of ways that certain things may happen, right? So it's pretty easy here, but maybe it's not so easy when I ask you some harder problems, right? Like, how many ways are there for there to be, 2 heads in 10 coin flips, right? So we're going to talk about that kind of combinatoric stuff in a couple of lectures. Let's go back to the more continuous stuff. So these were all discrete outcomes. What about cases like this where I've got a continuous outcome, right? So the sample space for this experiment 7 is basically, the set of x such that x is between 0 and 1, right? Which is a different way of just writing this same interval, right? Bless you. Here, the lifetime of my hard drive, well, it could be, dead right out of the box, or it could last forever, right? So that's basically the interval from 0 to infinity, open on the infinity side. And finally, let's draw S9 in a separate place here. So S9 is probably going to be something like I can kind of draw it like a shaded area where this is what x could be, and this is what y could be, right? Oops. So if x is 0, well, then y has to be 0, right? If x is 1, then y could range anywhere between 0 and 1. If x is a half, then y has to be between 0 and a half, right? So I can kind of draw in that the sample space is this shaded area here, right? Okay, so let me pause and ask. Questions or comments about anything I've said so far? Okay, all right, so we got experiment and sample space, right? And so I've already kind of mentioned the next key word, which is outcome, right? So the sample space is basically the list of things that could possibly happen, and exactly one of those outcomes happens on every experiment, right? So as we can kind of see here, we denote the sample space by usually an S, and then usually we talk about an outcome. I mean, there's no real standard notation for this. Sometimes I think the book uses this curly Greek letter, this is a zeta, as one of the elements of S, okay? But oftentimes in probability, we're not just talking about the probability of one given outcome, right? As we're going to talk about for sure, so in this experiment where I'm picking a random number between 0 and 1, it doesn't take a whole lot of thought to see that the probability of picking any given number has got to be 0, right? So the probability of getting a half is 0, exactly, because there's like an infinite number of numbers that the number could be, right? Instead, I'm more interested in talking about what's the probability that a certain set of outcomes happen, right? That the outcome was in a certain class of possibilities, right? And that's called an event, okay? So an event is a set of outcomes. Okay? That is a subset of the sample space S. Okay? So when things are really easy, right, when I've got a finite set of outcomes and I can count them on my hands, then I could really actually make a list of what are all the possible events. And so before I do that, let me just say that usually an event is something that you can understand in words, right? For example, let me just say some examples like this, like the die roll was even. That's an event. It consists of the set of outcomes 2, 4, and 6, right? Or I could say, we got more than 3 heads on 5 coin flips. And now depending on, again, depending on how I characterized the experimental procedure, that could correspond to somewhat different ideas, right? So for example, if all I was doing was counting the number of heads, then maybe my event would be 4 or 5, right? That would match the experiment I did before where I could count the number of heads. But if I was looking at more like the pattern of heads and tails, and I was looking at that pattern over 5 coin flips, I could maybe instead have an event that was something like, okay, I list the places where I got at least, 4 heads, right? And the question is, how many outcomes are there? I can see that I have 5 ways that there's 4 heads and 1 tail, and 1 way that there were 5 heads, and so there are 6 outcomes in that event. It all depends on how I characterize the sample space to begin with, okay? Or I could say something like, you know, X and Y differ by less than 0.1, right? So again, that's something that I could interpret in terms of this right-hand picture to basically say, okay, you know, I look at X, and then I look at X plus or minus 0.1, and that kind of corresponds to a band of, like a subset of the overall sample space, where the stuff that's in red are the places where X and Y are close together by less than 0.1, right? So it's a piece of the sample space. It's not the whole thing, right? So in general, like I said, when life is easy in the world of coin flips, you can actually kind of enumerate what all the possible events are, right? So let's just say that, you know, if S is equal to, say these are my possibilities, 1, 2, or 3, then what are my possible events, right? So I basically have to look at all of the sets of outcomes, right? So I could have, you know, 1, 2, or 3 by itself. I could have collections of 1 and 2, or 1 and 3. I could have collections of 2 and 3. I could have the event, you know, 1, 2, and 3, or I could have the empty set, right? So, for example, let's talk about how that might work in words, right? So maybe, you know, if I said the event is the probability that the, you know, the outcome is an integer, right? Then that would be this event, right? Because all these things are integers, right? Or I could say the probability that the outcome is greater than 4, right? Well, that's this outcome because there are no possible outcomes where things are greater than 4, right? And so probability, as we're going to talk about next time, is about kind of assigning consistent probabilistic values to each of these possible events, right? So kind of it stands to reason that, you know, the probability of this thing has to equal 1, right? One of these things has to happen, right? That's the definition of the experiment. And conversely, you know, if I look at the null event, right, nothing happened, the probability of that has to equal to 0, right? And then, you know, everything else is kind of up for grabs, but I do definitely have some, you know, life would be crazy if, for example, you know, I have to have the fact that the probability of this has to be greater than the probability of this, at least, right? So I mean, if I'm adding more outcomes to the event, then it can only get more likely that that thing happened, right? I can't make things less likely by adding more outcomes, right? So what we're going to talk about next time, basically, is what kind of sanity check rules does probability have to follow to make some sort of consistent sense, right? We're going to defer that until next time. And so you'll notice here that even though there were only 3 possible outcomes, actually there are 8, you know, possible events, right? And this 8 is equal to 2 to the 3rd. And so sometimes the set of possible events is called the power set, which you may have heard, I don't know where, in algorithms or something. I mean, this is a term that I heard somewhere, but I don't remember where. Basically, this is just like, you know, if I have 4 outcomes, I have 2 of the 4 equals 16 possible events. And so certainly to enumerate all the possible events becomes a huge pain when you have more than a handful of them, right? And it's impossible to count these events when you have, you know, a continuous sample space, right? But nonetheless, just to make it more interesting, I think that on the homework I do ask you to enumerate the possible outcomes or the possible events for one relatively painless example, right? Where you have to think about what are all the ways that things could happen. So to be consistent in probability, we have to be able to assign probabilities that make sense to each of these possible events, okay? We'll talk about how to do that next time. But I will say that it's easy to think about in terms of discrete outcomes, right? Rolling a die, flipping a coin, that kind of thing. It's a lot harder to think about in some sense for these continuous events, right? So for example, or these continuous experiments, right? So for example, if I look back at my thing, which I can't find, oh, here it is, it was right on top. So if I look back at these these experiments, right? You know, what is the set of possible events here? It's kind of hard to visualize what that would be, right? So for example, you know, if I have a number between 0 and 1, let's just say that, you know, I realize you guys are not all like, you know, PhDs in mathematics, so let's make it really easy and just say that the events that I care about assigning probability to look like, so like kind of in continuous sample spaces. Let me just say that we care about assigning probabilities to what I would say unions, intersections, and complements of intervals. Right? So for example, I care about things like saying, okay, I want to assign probability, if we're talking about between like 0 and 10, right? I want to be able to talk about this event or this event. Oh, maybe we like this. Something like this, right? I want to be able to say, what's the probability that this happened, or this and that happened, or these things happened. But these are like relatively easy things that I can shade in on the line. So for example, this event here would be like, if this is 2, this would be like saying, you know, what's the probability that the outcome was somewhere in here or somewhere in here, right? Basically, you know, sizable chunks of the interval, right? You may be thinking, well, what else could there be? There are like really nasty mathematical, you know, intervals that would be possible to describe but impossible to assign probability to, right? So for those of you that are, for example, math majors, what we care about here is what's called the Borel field of events. And that's all I'm going to say about that, but if you're more interested, you can kind of read up on that. This is the kind of thing that you probably get if you were taking a class like real analysis, for example. Okay. So, any questions about things? Yes? Unions. Sorry, looks kind of like an M. Right? So this is an example of a union of events. Other questions or comments? All right. So let me conclude with, so you can see here that there's definitely some sort of like set theory kind of stuff going on here. So just as a reminder, this should all be stuff that's kind of familiar, but let's do a quick set theory review. So set theory review. So if I've got my sample space, so usually I can kind of think about the sample space as a box, right? And I can think about an event as a region of this box, right? So, you know, so here's an event A. Maybe I'll use my thicker pen here, right? So here I've got this event. It's sitting inside the sample space, and I would say that I could have an outcome X that is in the event, right? So I'd say that the outcome X is in the event. That's what this little E means. But this outcome is not in the event, right? That's kind of standard set notation. I could have multiple events. So for example, I could have a event like this, A, and another event like this, B, and here I would use the notation that the event B is a subset of A. Okay? I could have two events and I could look at their union, right? So if this is A and this is B, then the union of those things is everything that happened in either one of these events, right? So I could have A union B. And then, obviously, there's the kind of opposite, which is I have the sample space, and I have two events, A and B, and you know what's coming. I have the intersection, right? So this is, we got too many pens, A intersect B. I could have a set A, or a event, and everything that is not inside A is A complement, right? So if this is A, then what you're seeing here is A complement, this little superscript C. And before I move off of this, you know, if the two events don't have an intersection, right? So I could have the situation like this, where I have an event here and an event here, and there is no intersection, then I would say that A intersect B is equal to the empty set, or the two events are disjoint, right? So for example, you know, one event could be the die roll is even, the other event could be the die roll is odd. The intersection of those things is the empty set because both things can't happen at once, and the union of those events is the whole sample space, right? One of those things has to happen. And finally, I could have basically two events like A and B, and I could look at the part of A that is not in B. So something like this. This would be like A minus B, like set minus, like this. All right, so if you understood everything today, then you can do the first homework, right? So let me pause and ask, any questions or comments about this? Yes? How would I describe the second, this one here? This is a complement. Okay, so let me just write that down. Complement. Simmer down for a second. Other questions or comments? Okay, so